now that we've established some of the fundamentals of remote sensing and we discussed some of the terminology behind remote sensing, the other thing that Perry and John asked me to talk about are some aspects of land cover remote sensing. I think a lot of folks starting tomorrow will be discussing other elements of remote sensing and model data. But I'm going to be spending the next roughly probably 30 minutes discussing some of the land cover applications. So next slide. So here's a scale of South America. We're going to be zooming into Brazil. I think some of you are probably from there and probably quite familiar or you're from there. And that's really on scale of the United States, overlapping it. And we're going to be zeroing into one specific part of the Southern Amazon. And this is using Landsat data starting in, I believe it is 1985. And we're noticing the changes in land cover using the Landsat mission from 1985 to 2018. Just showing you some of the powerful things you can do with satellite imagery, especially when you have a long record of that imagery going back many decades. So we're seeing now the same date, 1985 to present, and we're seeing where the roads start being established in the Amazon. And then once one road is established, you can see that the correlation where other changes in land cover take place are usually radiating out from that primary road. And then this is showing the burned area associated with that. Yeah, I'm sorry, these are 2019 fires. Anyway, that's just showing you some of the powerful things you can do. Burned area is one of the things you can assess very quickly with satellite data. Burned area, you can use different parts of the electromagnetic spectrum. You can use the shortwave infrared as well as the near infrared, and you can create indices from that. And you can look at burned area by taking that index from using the shortwave infrared and the near infrared, and you can look at an image before the fire and then look at another image of the same place after the fire, and it'll show you very clearly where that area has been burned. Where I'm from in California, a lot of people are doing this. I'm from a state in the United States that's very susceptible to climate change. There's a lot of parts of the world that are, but this is just one of the many applications of using different spectral bands to be able to assess burned area. But you can also see that those same spectral bands, you can create those signatures, the chemical makeup of vegetation or roads or buildings, et cetera. You can start looking at the spectral signature of what those are. And then you can start mapping out land cover using these different spectral bands. And so that's what I'm going to be talking about in these next few slides, how one goes about doing that in mapping. So next slide. So I think a lot of discussion today, and I think hopefully throughout this whole week, we're going to keep emphasizing that we really don't want data. We're swimming in data at this point. We're swimming in information. We want to be able to do something constructive or actionable with that data. And so it's really turning those different spectral classes, spectral classes. And again, think about making a sandwich of many different spectral bands from one area of the planet. So it could be from, the green, the blue, the red, the near infrared, the shortwave infrared, the thermal infrared, just kind of stacking all those up and then plotting those out on a curve based on the reflectance of those different bands, and then grouping those pixels based on where they are on that graph. You can start grouping them based on the uniformity. So where are they grouped on those different spectra? And then you can start applying those different groupings to a specific land cover. It could be water, if that's what you're interested in. It could be vegetation like forest. Maybe it's urban areas, so where cities growing. You can start looking at those different spectral signatures and mapping them onto the planet. And so we do that with spectral classes, but ultimately what we want are these informational classes. So we're trying to take those spectra, that data, and then turning it into something that makes sense. Okay, so instead of just looking at spectral curve, we can say that's water or that's forest, et cetera. And so these are just categories that are being derived from these different spectra. And that's really the goal of the image classification, is that process of grouping those different spectral classes and then assigning them to an informational class. So next slide. And this is kind of what it looks like when you start mapping them out based on the different bands. In this case, we're looking at the visible, the blue, the green, and the red, but then also the near infrared, shortwave infrared, and then these are actually two different bands of shortwave infrared. And we can see the different curves of vegetation and then versus soil. And that's one of the ways that you can start distinguishing between different land cover classes very quickly. So I think we've already discussed this before, but objects on the ground reflect radiation differently in different wavelengths. We talked about how that's a spectral signature. So even vast groups, we could say like a forest has a spectral signature compared to, say, an urban area like a city. But depending on what type of instrument we have, we can actually start looking between different species. So maybe it's a conifer tree. So it has needles and it doesn't shed its leaves. It just keeps its needles all year. Or it's a deciduous tree. So in the fall and the winter, it loses its leaves. So we can start plotting those out based on the instruments that we have. And we can actually start differentiating between different forest types. And these are different ways of being able to do that, and just different ways of using different parts of the spectra to be able to do that. Next slide. And these are some plots that we're seeing. These are, again, that sandwich that we talked about. I'm referring to it as a sandwich, but we can look at it here. So we're looking at different spectral bands. The spectral resolution is one, how wide each of those bands are, and then also how close together they are. And in this case, you can see that there are big gaps in these different these plots. The reason for that is because the atmosphere absorbs or scatters a lot of the light, that's the incoming radiation, in these certain spectra. And so that's why it's advantageous when you're observing different land cover types that you're specifically, when you're building the instruments to observe them, that you're really trying to target specific wavelengths, because there's really big gaps in these different spectra where the atmosphere is just absorbing or scattering them. So we're not actually collecting those part of the spectra. So when they're building these instruments, they're very much mindful of what channels that they're targeting. And we can see here that there's a lot of differentiation, especially when we're looking at, say, vegetation. We can see in the green, vegetation is very, especially with healthy vegetation, it's more reflective in the green. That's why we can see healthy vegetation, and it's more absorbent. It's absorbing a lot of the red and a lot of the blue. And then we can see here in the near infrared, there's a huge jump in reflectance, especially with healthy vegetation. And that's one of the ways that we can quickly start differentiating vegetation from other forest types. And then we can see here with the water, it's much more reflective in the blue and the green, but then it drops off in the red, and it's near nothing in near infrared because so much of it is being absorbed, that light. And that's why typically water is blue and green, and so on and so forth. We can see soil, especially in the shortwave infrared, is very reflective. And even the humidity within that soil depends on how reflective it is. So drier soil is more reflective than humid soil. So these are just different ways of assessing different land cover types. So next slide. And this is one way of plotting the band 3. So in this case, this would be, the red band. And then this is band 4, the near infrared band. And we could see that in vegetation, it's very reflective in band 4, but it's not reflective because it's absorbing a lot of that, especially with healthy vegetation, it's absorbing a lot of that red light. Water is not reflective in either the red or the near infrared. It's absorbing a lot of that light. And then dry soil in both the band 3, the red, as well as the near infrared, it's more reflective, dry soil is. So these are just different ways of being able to plot these different land cover types based on the different spectrum. Next slide. I think we already took a look at this slide before. And then for those of you that went through I think all of us have been through the installation, QGIS is mentioned here as one of the softwares used to differentiate. There's many different software, but we wanted to show QGIS, one, because it's open source. So everything we're using in this workshop is publicly available, or it's open source or open access. So so it's not, you don't need any money to be able to access it. So this is just one software, an application you can use that can help you create these different spectral plots. So next slide. And this is showing the same thing I just did. Next slide. And so this is showing different types of vegetation. This is an example, but this is 7 different types of vegetation. It could be grasses, it could be different species of trees. And so this is trying to show you in the different bands how it can be a real challenge to start differentiating between different species based on the spectra alone. If you have when we talked about spectral resolution about 30 minutes ago, we talked about that hyperspectral resolution. That might help differentiate some of the different species, but a lot of research is still ongoing when it comes to that. But these are just different ways of plotting vegetation generally and how it can be, they can appear quite similar, but depending on the instrument, you might be able to start getting different signals from these different spectra. So next slide. And these are showing examples again, when you plot all the different bands, the spectra. So this is the reflectance again. So this is looking at reflectance off of the ground, the land surface. And in this case, we're looking at vegetation versus soil. And we can start looking at, there's a clear distinction, especially in different parts of the spectra that can help start separating that reflectance, that signal that we're getting at the instrument. And so that's how we can start plotting. In this case, we're using 6 bands. Band 6 for some reason is not shown here, but this is 6 different bands, and then the reflectance that you're getting in each of those bands. So this could be, blue, green, red, near infrared, shortwave infrared, et cetera, and how these are being plotted out. And that's how we can use different software like QGIS, but it could be any other type of software. Maybe you're used to using Esri products like Arc Pro. They do the same thing, but it's just different ways of being able to plot that out so you can start categorizing and giving informational classes based on the data that you're seeing. So anyway, next slide. And then when we start talking about multidimensional, so when we start pulling in more than 2 bands, say it's 3 bands, 4 bands, you start getting into n-dimensional space. And n-dimensional space just has to do with the number of bands that you are using and plotting. So this is an example of 2-dimensional space. Here's an example when you start going into, more 3-dimensional, et cetera, and how the software is actually starting to, cluster these different spectra based on where they are on their spectral curve. So next slide. And let's see, and so, yeah, to be able to start assigning categories or information classes, we need to start grouping those pixels some way. And we can do that based on the spectral plot that we saw. But we can also start grouping them based on statistics. So you can start looking at values of the anyway, we can start, the goal is to start grouping them in some logical order. And that could be based on statistics. It could be based on the spectral plots that we were assigning. And Natalia Costa, how are you? Anyway, so I guess I'll stop there. Is there any questions to this point? Either from in person or anybody out there online? We definitely encourage questions. Okay. Is somebody sharing their screen by chance or no? So I'm going to keep going for the sake of time. And so really the goal now is taking those different spectra and then grouping them. And again, I talked about doing that statistically, but we can also do it based on the training data that we have. We can either using machine learning techniques, or we can use it using different clustering techniques that are not supervised, so they would be unsupervised, or we can use a supervised technique, which is, say, a subject matter expert. That could be one of you that's trying to assign those information classes based on the imagery that you have, based on the different spectral bands that you're looking at. You can start grouping the different bands based on the, again, if they are, showing different spectra in, say, water or vegetation, you can start grouping them. And there's different methods to do that. One of the methods is supervised, which is very much a user-driven. So you are the one that's delineating that I am going to assign this area to water. I'm going to assign this area to vegetation. I'm going to assign this area to some urban landscape. And that's one way of doing it, which is a supervised. And unsupervised is you are letting some algorithm, and there's different algorithms that do this, to cluster those pixels that the algorithm thinks are based on the spectra again, that are have a relationship. And it's based on the spectral curve. And that would be, that could be grouping them based on the number of, you could say, I want to have 10 clusters, or you could say, I want 8 clusters, but depending on the number that you have, it will automatically use an algorithm to cluster those for you. These are just different ways of going about assigning information classes to the imagery that you have. So you can do this at a pixel by pixel basis, or you can do it on an object base. Thank you, Perry and Taylor. And so these are just different ways of going about doing that. And object-based is more looking at, it's more a way of segmenting based on the texture of the image. And it's really assigning the categories based on how the machine's algorithm is clustering or segmenting these, and then you're assigning different categories to that. Or you can do it using a pixel-based approach. But these are just different methods of ultimately achieving the same thing, which is our information classes. And there are entire courses you can take on this. When I was doing my undergrad, I was a TA, a teacher's assistant in a class, and literally the entire semester, they just learned how to do this. So the fact that I'm going through it in 5 minutes is kind of, it's crazy to think about, but there's a lot more that goes into this, but it's just important that you know that that there is definitely a human element to this. Depending if it's an unsupervised or a supervised, there is a lot of there's a lot of corrections that and a lot of influence that humans have to attest for the accuracy of the result. So next slide. And I think I discussed this. These are the different approaches, supervised versus unsupervised. Next slide. And this is just kind of a infogram showing how this plays out. So in a supervised, if you were a subject matter expert, you would be assigning, you would be grouping them. You would actually draw a polygon on the map saying, this is water, this is water, this is a forest, this is a road, etc. And you would be assigning those classes. And after you did that, based on the samples that you drew, the algorithm would then go through and apply those spectral signatures based on the training and apply that to the other pixels. And that's how you would get a result with those information classes. And then you would evaluate the result of that. And typically there's going to be an iteration, excuse me, typically you're going to need to iterate because you might not be as satisfied with the result. There's ways of assessing accuracy. And that was anytime you undergo one of these processes for classification, it's absolutely vital that you assess the accuracy of those results. And depending on that accuracy, you would need to iterate on that to maybe draw more representational samples of the different categories or the different classes, or you would maybe need to draw more of them so you can capture more of the variability within those different classes. And then the unsupervised is you basically, the machine uses an algorithm, runs clustering, you assign it how many clusters you want, and then it identifies those classes, and then you basically edit that and then iterate on that. And a lot of times, this is a useful tool if you are maybe not as familiar with the area, maybe you're not an expert in the area that you're working in, and you can start running unsupervised methods, and then start running supervised methods on that to be able to refine the results. So you might start out with maybe 15 clusters, and based on the results of that, you can then start, they call it cluster busting. So isolating different clusters and then reassigning values within them to be able to refine it more. So just different ways of doing it. Everybody has an opinion. I'm not going to go into what opinions are, but we'll go to the next slide. And this is basically showing somebody here is drawing samples, different training samples of these different pixels based on some subject matter expert is identifying this as known water, known conifer, and known deciduous. So this would hopefully be somebody that's familiar with that area, that knows this is a forest, that knows this is a, so on and so forth. And they can, with confidence, be able to draw those samples. And based on the samples that they draw, and they would draw more than just one of each, they would draw many to capture the variability within them. And then ultimately, they would train on the spectral signature of those sampled pixels and then start deriving different information classes. Next. And then this is basically showing that same thing. The spectral signature of each pixel gets matched with the training signatures, those polygons, and then the image is classified accordingly. And then ultimately you check the accuracy of that. So next slide. And this is kind of a rules of thumb when you're going about doing this, best methods, so to speak. So if you're using n bands of data, let's say you have 5 spectral bands that you're going to use to classify this, then you would want 10 times the number of bands. So you'd want, say, at least a cluster of 50 pixels representative of water, and you'd want many of them. You'd want at least 50 pixels if you're working with 5 bands of, say, vegetation, et cetera. And then the size of that must be large enough to provide accurate estimates of each class. The location should be represented by several training areas positioned throughout the image. You don't want to collect all of your training samples in one area. You want to spread it out, so you're getting a lot of heterogeneity throughout the image. And then the number, you want 5 to 10 per class minimum. So yeah, so if you had 5 classes you wanted to classify, then you would want 5 to 10 training samples per class. And uniformity. So each training area should exhibit unimodal frequency distribution for each spectral band. Next slide. And this is just going into more about how you can see here, this is selecting one polygon around this, but there's a lot of heterogeneity in this area. You'd want to select an area that has more homogeneity, that's more characteristic of that one area based on its one spectral signature. So in this case, they are, instead of taking one, which has a lot of variability, you would try to capture multiple so that it's capturing each unique spectral signature of each land cover class. So next slide. And now I'm going to switch over and I'm going to give an example. You can go to the next slide. I'm going to give an example of a tool. I'm going to take a show of hands. How many people have heard of Earth Engine before? Earth Engine, some of you? Great. Oh, okay, good amount of you. Great, wonderful. So the next couple examples I'm going to show, because I think I've been talking long enough. I think now is a good time to start showing some examples, some demonstrations, and all this code, the links to this code you have access to, both in the English and the Spanish versions. So if you have an Earth Engine account, yes, please. Yeah, I see a question.
Dame un segundo. Sale el micrófono para producción. El proceso que pasaste, que explicaste hace ratitos, ¿es con el programa QGIS lo que se hace o con qué software, digamos? ¿Y se utiliza la imagen Landsat?
Yeah, great question. Thank you. Thank you so much for that question. It's a really good one. It's software agnostic. You're not limited to one application or one software. QGIS, ArcPro, Earth Engine. There's a lot of open source, there's a lot of proprietary software, but all of them will allow you to do this. And a lot of them use the same or similar algorithms. So we talked about the unsupervised or supervised. A lot of them are using similar or same algorithms to be able to start parsing those out into different informational classes. So you don't need to use just one software. I prefer QGIS myself, just because I like to use open source software. And in the program that I'm in, the RSET program, we have people from all over the world. It's very international, and not everybody has access to Esri software, which can be very expensive. So we try to use in my program, open source, publicly available, free software. But you can absolutely, if you're more familiar with, say, like a Arc Pro, you can absolutely use that to do this this method. Yeah, it's a great question. Thank you. Okay, anybody online? Anybody with questions? Did you have a question? Okay.
Okay.
Okay, great. So I guess this is a reminder. I think Perry sent this out, but this is a reminder that if you wanted to follow along either today or in the future, that one of the requirements to using this software is you need to create an account with Earth Engine. If you have a Gmail address, that's one way you can do it. You can use, if you have like an academic email address, you can use that too. But the important thing is you do need to create an account. It is free, but you do need to create an account. And the demonstrations that I'll be showing today will be using Earth Engine. And so next slide. And so what is Earth Engine for those that aren't familiar? It is, so this is kind of jargony when I say raster. Raster just basically anything that is made up of pixels. So think of most imagery that you're used to seeing. It's going to be raster based. It's going to be made of pixels that have columns and rows delineating some dimension, like how many, what's the width, what's the height, etc. And so that's what this word means, raster. And it's a cloud-based raster computing, and it greatly lowers or removes barriers to working with imagery, and especially with a large volume of imagery. And that, as I mentioned earlier in my previous presentation, that in the past, even 10 years ago, we were hungry for more data. We wanted more data. Now the problem is we literally are being overloaded with data. So the methods that we had in the past are not able to keep up with processing the voluminous data, the time series going back for decades. We're talking millions of images that you want to process, and you're not able to do it on your personal machine. Maybe you work in an office or maybe a bureaucracy where you can do that, but a lot of people don't have that opportunity. So the great thing about Earth Engine is it is free, but you have to create an account. But you're able to access the entire records of all this imagery, and you're able to process it in seconds, which is incredibly powerful. And so finally, the algorithms are catching up to the data. So before we used to take the algorithms, the data to the algorithms. Now we're able to take the algorithms just to the data because all of it's being stored on Google's cloud. And so Google is hosting all the data. They're providing the application programming interface, or API. They're providing that to be able to interact with the data, to process it, to analyze it, to visualize it, to do all of that. And it does take some coding, but it's a lower bar to be able, with literally just a handful of lines of code, you can do so much computing power in just a handful of lines of code. And I'll be showing that very soon. And it's also personal computing capabilities. And the great thing is it's free for scientists, researchers, and developers. So I know there's developers out there, certainly a lot of scientists and researchers in the crowd. So anyway, it's a really great platform, and it's definitely taken off. And a lot of people are using it just because it's so powerful. Next slide. And again, I think I mentioned this, but it takes advantage of Google's cloud computing capabilities. So you're no longer having to download any data. You're removing that. All you're doing is you're basically getting the results. What do you want? What's that information you ultimately want to get? And then you can actually make some decision. You don't need to go through downloading and getting, purchasing software or downloading software. There's nothing wrong with that. I still do all that, but it certainly streamlines that whole workflow. And it's really good for accessing satellite data, especially a lot of the European Space Agency, as well as the NASA satellite data. It's really great for that. And a lot of the algorithms that we're used to using, I'm sorry, I forgot your name, but you were just talking about QGIS. A lot of those algorithms are actually within the Earth Engine script. So you can actually do a lot of that in Earth Engine as well. And they provide an API, an application programming interface. And you can also, if you're more familiar with Python, which I'm sure a lot of you are, they also provide an option to interact with Python API as well. So next slide. It's just a kind of a image showing how it's all basically all this data. And actually the folks that started Earth Engine, they were brought on, they actually used to work at NASA. I actually got to see a talk. They came to the place where I work many years ago now. It's probably 7 years ago. But they came and they were actually hired by Google because they'd been working with satellite data for many, many years. And Google hired them on to be able to launch Earth Engine. And so they're one of the ones that are really getting us off the ground. But they just have such a vast catalog and they're constantly adding to it. So anytime new imagery is being pulled down from different platforms, they're ingesting it on their servers so that we can ultimately use it. So next slide. And okay, so the JavaScript API, which is what I'm going to be demonstrating today, is one of the ways to interact with the data. But I think I mentioned a Python API is also available through Google Colab, Google Collaboratory. So if you have a strong preference for Python, which some of you might have, you can certainly do that. Yes, I have a question in the back.
I'm wondering if we are familiar with R and not Python or JavaScript. Do we have any chances here?
It's a great question. So currently it's just a Python API or JavaScript API. I've not heard anything if Google plans on providing more options. I'm sure a lot of the user community would prefer that, but currently there's just those two APIs that they're working with. But it's a great question. Thank you. And I would say that so here's again, everything in life is about repetition. If you do the same thing every day, you're going to get familiar with it. You might have your own programming. So a lot of people say that the Python API is more difficult, but something tells me if you did that every day for a month, you'd probably not find it as difficult as maybe the JavaScript API. So it's all relative to everything you're doing. And just like anything, repetition is you're just going to get better at it. So anyway, next slide. Great. And then so these are some of the uses of Google Earth Engine for satellite imagery analysis. So you can automate data processing and display. So you can create these scripts and very easily just share that link with friends or colleagues, folks that you collaborate with, and they can take that script and continue to build off it. You can create repositories, shared repositories, same as when you pulled from Perry's GitHub repo. You can do the same thing with, they're basically using the same Git on the back end to be able to share repositories with colleagues. So you're able to do that, but you're not necessarily having to go through the steps that you all did to be able to pull that. They're just constantly updating that in the background. Near real-time monitoring. This really depends on the mission. Some of the missions are more current. They're updated more often than others, but it is very useful for near real-time because they are constantly ingesting recently observed satellite data. And then you can apply a lot of machine learning algorithm applications to the data as well. And then there is a graphical user interface implementation. It's probably not the most common. It's much more robust to use one of the APIs, but there is a user interface implementation, but it's not as powerful. Next slide. So this is an example of using is a time series of MODIS and DVI. I think Perry's going to be discussing some of MODIS tomorrow. And so anyway, this is just showing you the power of MODIS imagery, which is collected on a daily, 1 to 2 days, actually, it depends. Typically on 1 day, but sometimes it can be up as much as 2. And because you have that temporal resolution, you're able to observe things as, say, the seasonal pulse of the seasons as they migrate north and south within equatorial Africa. You can see in Southern Africa and in Mozambique, how it greens up and how it shifts north and back. You can see how in the Horn of Africa, and especially up in Southern Sudan, how every season, how it kind of pulses up and back, and how the Sahel goes from, quite arid to quite green just in a matter of months when the monsoon season hits. So it's just really powerful. This is, we're visualizing this. It's really powerful to be able to see that, but there's a lot of stuff you can do in terms of analysis, in terms of, how is this season compared to all the previous seasons, or, how is this one area compared to other areas, depending on that season or other periods of time. So there's a lot of great, you can start correlating this with environmental variables. So if soil moisture or precipitation or these other variables that are contributing to, say, vegetation greenness, which is what we're looking at. So anyway, it also takes a lot of the heavy computation and it puts it on their cloud servers, which is benefit. Also for large areas, for landscape time series analysis and for change detection, it's incredibly powerful for summary statistics. And then also when I talked about anytime you do a classification, you always have to do some type of accuracy assessment, and you can also do that within Earth Engine as well. So next slide. And so these are some of the examples of the data. I highly recommend, we did provide links, or I provided links in here for the data catalog, and you can explore for yourself. And it's not just Earth observations. There's also model data. There's also socioeconomic data that people are updating into there. So I highly recommend that you go through the catalog for yourself. Maybe you're more focused on, water resources, and there's whole data sets that are just for your area of interest that are on here. And you can filter the data sets based on your interest. So this is just an example of, say, Landsat, and this Landsat archive is going from, the last 50 years, from 1972 till present, and so you can get the raw images, the top of atmosphere, or the surface reflectance. I didn't go into those nuances, but for the sake of time, I'm going to keep going. So those are some of the data sets, and then you can keep next slide. And then also starting about 8 years ago, actually 9 years ago, the European Space Agency started launching a series of satellites, which they call the Sentinels. And these are observing land processes, but they're also observing oceans, they're observing the atmosphere. So they're really approaching it from a system of systems approach, which is how NASA is now going about their missions as well. And this is an example of one of the Sentinels, Sentinel-2. So this is observing both the land as well as the any water resources on land as well. And this has a better spatial resolution and temporal resolution than Landsat. So this is just one of the really nice data sets that you have the entire time series for. Next slide. And then Perry is going to be demonstrating some of the MODIS data tomorrow, or the imagery, I'll say. But this is example, and they have everything from daily to 8-day to 16-day composites. There's so much, and I highly encourage you to go and see for yourself. All the links are on these slides, and you can go and see for yourself. Next slide. And this is a shameless plug for some of the RSET trainings that, once again, I am with the RSET program, so I would be remiss not to plug some of the trainings that we're doing. But we've done a lot of trainings using SAR data. SAR stands for synthetic aperture radar. And one of the most widely used missions that collects the SAR imagery is from the Sentinel-1 mission, which the European Space Agency launched. The first one went up in, I think I want to say 2015, and they launched a second one. Unfortunately, one of them is no longer working, but another one is working, and they're about to launch another one to complete that constellation. But this is, if you want to learn how to work with radar imagery and SAR imagery, do go to the RSET website. Actually, the woman that leads the trainings is from Panama. And so not only do we translate the materials, but the trainings themselves are actually led in Spanish as well. So, and we have a lot of trainings that are led in Spanish because 4 different people on our team are native Spanish speakers. So definitely worth checking out the RSET trainings. And this one specifically is looking at forest mapping and monitoring with using SAR data. And all this is, the presentations and the materials are in Spanish. Next slide. And again, this is looking at different applications for burned area. I think I talked about this earlier, so we'll skip on. This was one that we did looking at mangrove mapping. And this was using anyway, different methods to map mangroves using both optical as well as the SAR data. So next slide. And this is just showing an example of using Earth Engine for land cover mapping. In this case, we were using just 3 information classes. In this one, we have 6 different information classes. Next slide. And this one is using some jargon. This is saying NDVI, that stands for Normalized Difference Vegetation Index. It's a way of assessing, it's a way of getting a signal of the greenness of vegetation. And the Enhanced Vegetation Index, or EVI, is more appropriate in different land cover types, especially if it's a dense forest, say like a rainforest, where you have a lot of dense greenery, then this index would be more appropriate. But they're just different ways of assessing the greenness of the vegetation. And so anyway, there's all of this is available through the Earth Engine application. Next slide. And this is showing, so this is kind of leading into my demo. And this is showing some of the different land cover products. So if you wanted to be able to take a product and just start working with it, instead of going through the steps of, subsetting the imagery and then creating training classes and then running a classification algorithm and then assessing the accuracy. If you wanted to take one of the, we call them analysis ready products, which is really what RSET is trying to get across, because really you want to be able to take a data product and be able to do something to derive a decision. These are some of the options that you have just through Earth Engine. These are classified and validated to a certain level of accuracy. And in my demonstration, I'm going to be showing or demonstrating how you can both access and start visualizing this one data product, this European Space Agency, the ESA World Cover 10 meter. And here, this link here is a link directly to the all the different land cover tagged data sets on Earth Engine. So next slide. And so now it's going to lead into the demo. Next slide. And again, all this has been translated and you have access to it all, but the code for this demo is all you have to do is create that Earth Engine account. And if you click on this link, it should take you to my repository where you can use the code however you want. It is freely available. I hope you use it. And then for the data set in which I adapted the code, if you want to learn more about the source of that, you can click here and how that data set was generated. And so this is land cover for the year 2020. And it's provided by this data set, and it's provided by the European Space Agency using both Sentinel-1 and Sentinel-2 data. So that's both the optical data as well as the radar data. And that's how they generated this forest class. And it's generated to a 75% overall accuracy. And it's been validated by an independent source. So in this push for open science, there's a group called CIOS, Community on Earth Observing Satellites. It's an international community, and one of their goals as they push open science is there always has to be an independent validation. And so there's actually a group out of the Netherlands that validated this global land cover data set, and it was derived from millions of different satellite imagery from both Sentinel-1 and Sentinel-2, and it was actually generated from a consortium of different people, academics, federal bureaucrats, et cetera. And so that's how this was generated. And so I'm going to go ahead and step over here and demonstrate how in just a handful of lines of code, you can really start confining and constraining your analysis to your study area. So in that case, I decided to use the La Plata River Basin because I believe everybody in here is probably more concerned about that river basin than any other one. So I'm going to quickly walk you through this code, and you're going to see in just not that many lines of code, we're able to generate a map on the bottom, such as this, which is a land cover map, which has been subset to the La Plata River Basin. Yeah. So again, this is just anytime you work with code, hopefully best practices, you always comment. So hopefully if you're coding, you're used to doing that. This shows, this code is free and open. It also shows the source of that. So if you wanted to read more. And this first line of code is establishing a variable. So a lot of times when you code, you define variables. And in this sense, I'm defining a variable, and I'm going to call that land cover. And in that variable, I'm basically taking the Earth image collection for this European Space Agency world cover version 100, which is based on the year 2020. And then I'm going to define a new variable, which I'm calling clip. And I'm going to take that collection, that 2020 land cover map, and I'm going to clip it based on an asset, which I've defined up here as La Plata. And that's basically, I'm going to use a jargon called a shapefile. And if you don't know what that is, it's basically a polygon that delineates an area of interest. And that polygon in this case is the boundary for the La Plata drainage basin. So I define that variable La Plata as that shapefile or that polygon, that boundary. And that's what I'm using to subset or to clip the global map, because this data set is global. And I'm using that land cover, that shapefile to clip it to just that area of the La Plata Basin. So in just those 2 lines of code right there, I've already taken that data set and clipped it to the area of interest. It could be any area of interest, but I chose La Plata just because I thought that might be of more interest. And then I defined a variable visualization, which basically defines the colors of all the different information classes. And then in this next line of code, I set the center of the map to be the shapefile or that polygon, which would be the La Plata River Basin. And then these next lines of code, which I commented, are adding map layers to the map window. So you need to use a function called map add layer. And then I'm saying I want to add that clipped, that subset image of just the La Plata River Basin. And I'm going to visualize it with the variable I defined just above, this variable visualization. I'm going to use that visualization. And lastly, I'm going to give it a name. I'm going to give it a name called land cover. And then this next line of code where it says map.setOptions is using a satellite image as a base map. I'm sure a lot of you are familiar with Google Maps, and the default is not an image. It's their default map window, that map, whatever that is. I don't know what the better way to describe it, but this is basically defining and saying, I want to use imagery as the base map. So when I have that land cover map, that base map load is going to be just some satellite imagery. At the extent in which we're looking at it now, it is probably publicly available, but the way that Google tiles their map, the more you zoom in, it will go to proprietary commercial satellite imagery they probably had to pay for to use as their base map. But the way they tile it, this is probably Landsat or Sentinel data. And then I started defining, I defined a new variable, and that was, I called it viz params. And that's basically defining the visualization I want to give to the polygon. So that's what all this line of code does here. And then I use that function again, map.addLayer. and I added that shapefile. I added that polygon to the map window, which is down on the bottom, and I used the variable visparams and the parameters that were defined. So just in those handful lines of code, I've already taken a global data set, subset it to just the area of interest, and I've also added the shapefile and in not that many lines of code. The next block of code here is creating the legend for the information classes. So again, we have spectral classes, but remember, we ultimately want information classes, and this is basically creating that legend. So it'll appear and use the same color relationship between the visualization I defined above and the, where is it? Here it is. So I'm using the palette here to match the visualization I defined above, and I'm also matching the information classes. So the name of the legend, I'm matching each information class with the category, the name of that. And that's basically, this whole chunk of code is just trying to make a pretty legend. So I would think probably the most lines of code in this entire thing is not even dealing with the imagery. All it's trying to do is make a pretty legend. So it's a little ironic that probably the hardest work I had to do was just make a legend, but it just goes to show how powerful it is to take a lot of data and do a lot with it and not much code, and then really get a headache of just trying to create a legend. But anyway, it doesn't matter. You have all that. It's in the code. You can do it whatever you want. Give the name to that. This is a function. That's a loop function to basically go through and assign the different information classes to the different colors for those information classes. So that's and then I basically used a function to add that to the legend. And then this last block of code, which you can uncomment, you have access to all this. If you wanted to export this, or if you wanted to change or edit the code above, however you wanted, but if you wanted to export this to maybe bring into like QGIS, or if you wanted to bring it into say like Arc Pro or something like that, you can use this last block of code, which I'm highlighting here, which is already commented out. And anyway, yeah, you can basically uncomment that. And if you have a Google account, you're automatically given 15 gigabytes of storage on Google Drive. You can purchase more if you want, but you get 15 gigabytes for free, and you can basically export that to your Google Drive. And then you can bring that into a GIS, a commercial, and open source, whatever. So that's basically what all that code is doing. And you can do it all pretty straightforward. And I'm going to go ahead and click run. I know it's already done, but this is basically going to take that global data set, center it on the La Plata drainage basin, clip it to just that basin, and it's going to create a legend using the visualization, the colors, as well as the information classes so that it will appear. And cool thing about this is, you know, you can zoom in. Oh, shoot, where's the, oh, and here's another thing. You can, yeah. So this is, if you want to play around with the layers, so you can see, this is one of the shape files. You can turn that on and off. You can turn the land cover on and off. And anyway, where's the zoom? So does anybody here have an area of interest that they're interested in? Any part of the basin that you want to take a look at? How about somewhere up in, well, I'm sorry. Okay, let's do it. Let's run. Okay, So we are now at the Brazil-Uruguay border, and so anything in red is going to be some urban built-up environment. So it's probably going to be buildings, roads, non-impervious surfaces. So any built-up environment, concrete, steel, brick, glass, and then anything in dark green is going to be forest. Anything in this lighter shade is going to be cropland. So I'm going to zoom in a little bit more, and then we can turn it on and off, and you can start seeing how accurate this is. And this is just through visualization. There's a lot other metrics you can look at, but one second. And because this is 10 meter, which is pretty good for publicly available data, you can really start zooming in a lot. And the base map that they're using at this extent is very high resolution. It's probably commercial imagery, but we're going to turn this on and off and see how good it did. And again, this was done using both Sentinel-1 and Sentinel-2 data. So that's both radar data as well as optical data. So depending on what your area of interest, and thank you for suggesting that, I really appreciate audience participation. But this is just one way. If you're, depending on where your area of interest is, you can zoom into that and really start drilling down a little bit more.